In question 6, we have 1,3-dimethyl-benzene. So this is a 1,3-dimethyl-benzene. So 1, 2, 3. Because if you go the other way around, 1, 2, 3, 4, 5, that 1, 5 is going to be bigger than 1, 3. So 1, 3 is the correct name. What you have done is you have done a substitution here. So you have done a substitution. This is what you call the type of reaction, because this is as stated in the AS introductory chemistry, the terminology. The mechanism is going to be electrophilic substitution. In the current A2 syllabus, you will learn this as Friedel-Crafts alkylation. Friedel-Crafts alkylation is not the mechanism. It is not the type of reaction. It is the name for the specific reaction there. And then this next one is what you call Friedel-Crafts acylation. So that thing there is Friedel-Crafts acylation informing that acyl group there. You must have done a substitution again. Your type of reaction is substitution, but your mechanism is going to be electrophilic substitution on the benzene ring. We don't call it Friedel-Crafts acylation, even though this is the name stated in the syllabus, because it is not a mechanism. It's just the name of the reaction there. So the rest of it, you have done another electrophilic substitution there. So the very last step 3, the type there again is substitution, as you have substituted another 2 hydrogen on the benzene ring with NO2 and NO2. This mechanism is again electrophilic substitution, but in each of these electrophilic substitution, you have used a different electrophile in order to substitute onto the benzene ring. Here you have used an alkyl group. Here you have used an acyl group. Here you have used an NO2+. So let me just write that down. You have introduced an NO2+. You have introduced a COCH3, an acyl group. This is called an acyl group. And as for step 1, you have introduced carbocation and alkyl group. This is alkylation. This is acylation. This is nitration, nitro group. Okay. Now, the only byproducts of step 2 is HCl. That is because you kick out the H+, and then you kick out the Cl- from the acyl chloride. So suggest the reagent that was used. It has to be CH3COCl. They are not asking for the formula. They are not asking for the name. You could have given the formula like that, or you could give the name, but the name has to be correct. It is a 2-carbon acyl chloride. The name is called ethanoyl chloride. If you choose to give the name, it has to be spelled properly. I would always go for the formula unless I have no choice. The next question suggests the type of reactions occurring in both step 2 and also step 3. They're looking for the type of reaction, not the name of reaction, but the type of reaction, which I've stated both of them are substitution reaction there. You have substituted the hydrogen of the benzene ring with an electrophile. This is an acyl group electrophile. This is a nitro group electrophile there. What is the reagents and condition needed for step 3? This is in your case study, obviously, nitration. So you need concentrated HNO3 and also concentrated H2SO4 in order to give you this electrophilic mixture that contain NO2+. And the conditions, well, you need to reflux these at very high temperature, around 50 to 60 degrees Celsius. Suggest the structures of the two products when A is reacted with alkaline aqueous iodine. Alkaline aqueous iodine is the classic iodoform test. So iodoform test will give you a yellow precipitate. This yellow precipitate is triiodomethane. You also know it as iodoform triiodomethane there. And where does this carbon come from? It comes from this methyl ketone. So it's a test for CH3CO or CH3CHOH. So this carbon has been chopped off, it's been fragmented from the original part of the molecule. So that's CH3CO carbonyl or CH3CHOH as part of alcohol chemistry. What do we have in A? We have this mass ketone there because we have this CH3CO. So what is being fragmented will be this bond here. So you know that thing there will be lost as CHI3. So what you will get then is you will oxidize the ketone essentially, and you will get a carboxylic acid. However, you are in basic condition because it has to be done in alkaline aqueous iodine. What you will get will be the carboxylate salt. So what I can do is, this is blah blah blah. So let me try and draw the product on this side, on the left hand side. Nothing wrong with the nitro group, so it will not react. Nothing wrong with the alkyl groups, they will not react. So what will react is this thing here. So the CH3CO, now you have O minus, and you are in alkaline aqueous conditions. They did not mention what is the base. It could be potassium hydroxide, it could be sodium hydroxide. We do not jump to conclusion, therefore I don't write the Na plus there. I just know that it's under basic condition, and under basic condition I will not get the acid product. Instead I will get the salt of the acid because this is under alkaline condition. We don't know whether it's Na plus or K plus. They never mention what alkali they use unless you assume. An assumption can be dangerous unless you know exactly what you're assuming there. Okay, triiodomethane, this is called the iodoform. This is the yellow precipitate. It comes from that CH3 group that has been fragmented from that methyl ketone CH3CO, get chopped off there. The ketone get oxidized somehow. Under these conditions, you get a carboxylic acid that get deprotonated to give you the salt under alkaline condition, and that terminal carbon there become iodoform yellow precipitate. Some more chemistry here. So 1,3-dimethylbenzene, you can also use it as a starting material, and you react that to form dicarboxylic acid. So this was 1,3-dimethylbenzene, and now you get 1,3 is that 1,3? How do I name it? This one should be benzoic acid. I guess this is a dibenzoic acid. 1,3-dibenzoic acid. So a CO2H bonded to a benzene is called benzoic acid. I've got 2 CO2H on a benzene at position 1 and 3. This one on the other hand is called 1,3-diphenylamine because, you know, amine bonded to a benzene is called phenylamine. So what I get is diamine, but they are both phenylamine, so it's 1,3-diphenylamine. Now this going to this, the arrow matters, so focus on the arrow. So this is right going to left. So what happened is loss of oxygen, gain of nitrogen. Look at the nitrogen atoms. It gains hydrogen, it loses the oxygen. This is very clearly step 2 is your classic reduction of your nitro group, which you can easily do with what's that thing there, reduction of nitro. You use SN and HCl aqueous and reflux, but this is in acidic conditions, so the concentrated HCl actually, not aqueous HCl, I beg your pardon. So con HCl reflux with tin will reduce the nitro specifically to the phenylamine, but this is an acidic condition and it will protonate on the phenylamine, which is weakly basic. So what happened then is you have to add excess NaOH afterwards because you have to neutralize the H plus and return you back to the diphenylamine because they will not react further with NaOH. It will just take away the H plus that the phenylamine already protonated in order for you to give you this one here. This is an oxidation of the alkyl side chain on the benzene ring. So the alkyl side chain, so oxidation, very special oxidation of the alkyl side chain of benzene as stated in the syllabus, and you just do this with acidified KMnO4 and reflux. Not too sure if they're asking you for the conditions or not, but they are asking us to draw the structure of one repeat unit of this condensation polymer. In fact, that is the next question actually, what kind of polymer this is. You're going to form an amide. So straight from IGCSE or O-level chemistry, the very last few topics involve polymerization. So carboxylic acid and this NH2 will come together. They call it condensation. You will lose the H and you will lose the OH from the acid. You will lose the OH from the acid and the H from the amide. So what happened then is you will get something that looks like this. If I draw the carboxylic acid first, CO like this. The new bond that you form will be this one, the pink one. And this new bond is connected to the orbit of the molecule, the NH. And then this is bonded to something else. And then the other one is bonded to something else. They are not asking us to draw the repeat unit fully displayed. So I am not going to draw the repeat unit fully displayed, because sometimes they will say show the amide bond fully displayed. So you have to show the CO and H fully displayed, including the atom. But they didn't say that here, so I should be able to leave in the skeletal formula format like this. This is from the dicarboxylic acid. This is the new amide bond that you form. This is also another amide bond that you form, but this will already be bonded to the other carboxylic acid fragment on the other monomer. So there are two monomers, 1 and 2, and these two monomers, now give you this repeat unit, which consists of one fragment of this monomer and the other fragment of that monomer. You get amide bond formed as a result of condensation reaction. This is a condensation polymer. In this condensation reaction, two molecules come together and you kick out a small molecule, because in your syllabus, you will know that condensation is a two-step mechanism. Condensation is two-step. The first step is what you call nucleophilic addition from the AS chemistry, and then elimination of a small molecule, which is usually water. But then, you can eliminate H2O or HCl if you use things like acyl chloride instead of the carboxylic acid, because acyl chloride is far more reactive compared to carboxylic acid. Here you use carboxylic acid, and so you're not going to kick out HCl, you're going to kick out water. The carboxylic acid lose the OH, they combine with that H there, you will get water. I will just write down H2O as the formula there, because they didn't ask for the name, they just asked for what is the product. I could just give the formula there. What is the reagents and conditions for step 2? Step 2 was the reduction of the nitro group of benzene into phenylamine. In the old syllabus, they used to just stop there, but I am pretty sure in the 2022 syllabus, they are now far away that students know that this is basic group, and they will protonate if you just do it in con HCl, and as such you have to neutralize the excess HCl by using excess NaOH, so that you will take away the H plus from the phenylamine that will get protonated previously, and then only then you will get the free form of the acid, and only then you will get the free form of this diphenylamine there. So I'm just gonna copy paste that so that I don't have to write. Actually, I can write the whole thing. This is reduction of the nitro group of nitrobenzene. So as I did mention, we can start off by talking about tint and concentrated HCl. They also want the condition, so reflux that. Then very importantly, then you have to add excess NaOH so that you can neutralize all the concentrated HCl and give you back the phenylamine form. In this next question, suggest how and why the properties of the polymer might change if you replace some of the diamine with 1,3,5-triaminobenzene. If we replace some of the diamine monomer, so what's going to happen is you are going to get that NH, and now you're going to get CO. What's going to happen? What is going to happen? So that thing there, it looks like it's going to be bigger because it's going to extend in this direction. It's going to extend in this direction. It's going to extend in this other direction as well. It's going to extend in all three directions. Previously, it will just extend in two directions, here and here. So it will change the structure, I guess. How and why the properties might change? Well, we have extra NH2 group that can polymerize with the dicarboxylic acid in another direction. So what we can see here is that when they polymerize this way, we get a symmetrical structure, right? When we get a symmetrical structure, I wonder what I can say. I wonder what I can say. I will get amide, and this thing are amides. So amides has lone pair on the nitrogen. Yes, they are not basic or acidic. They are neutral. Amides are neutral. And we know that amides can form hydrogen bond because you have hydrogen bonded to electronegative nitrogen. They can form hydrogen bonds among the layers of the polymers. So the fact that you are branching out with more of this polyamide group, because you can form more polyamide in the other direction, I can imagine that hydrogen bond will be stronger. So the properties will make it more soluble in water, I guess. Maybe. All right. Polymerize with dicarboxylate in another direction. More polyamide group or more amide group can form more hydrogen bonds, can form stronger hydrogen bonds between themselves. And if they can form stronger hydrogen bonds, what can we say about properties? So perhaps you can say higher boiling point, perhaps higher solubility, perhaps. These are just suggestive kind of question, how and why. I'm just thinking about more of that polymer that extend the other direction. They can form hydrogen bond, more soluble in water due to hydrogen bond with water, higher boiling point because of stronger hydrogen bonds between different chains of the polymer, between different molecules of the polymeric chain. For that, just 1 mark to sum up these 10-mark questions on polymerization and some A2 organic chemistry there.